When this guy is swimming through the water at some velocity, and the water is moving down the stream at a different velocity, you can combine those two velocities to find his resultant velocity relative to the ground under the water. And vectors is a technique that will allow us to do that fairly easily. Before we get into vector quantities, we have to remind ourselves everything we know about scalar quantities. And we know a lot about scalar quantities. You might not just recognize what the word scalar means, but a scalar quantity is a quantity that involves only the size, the bigness, the how much, or what we call the magnitude. So for example, we just spent a lot of time talking about speed and velocity and stuff, but that's just how fast you're going, how much mass you have, how much time has elapsed, or how much volume you have. And that's the how much. But that's really all it involves. In fact, if you were to try to put direction onto scalar quantities, it would just be completely nonsensical. If you were to try to follow a recipe, and for sugar you need 3 tablespoons south, flour 2 cups to the right, salt 1/4 teaspoon up, it makes no sense to put direction onto quantities that involve only magnitude. Vector quantities, however, are quantities that involve both magnitude and direction. So if we know already that speed is a scalar quantity, then we can probably figure out that velocity is a vector quantity, because velocity was different from speed, and that velocity required us also to state the direction. And if we leave off the direction for those types of quantities, it also is nonsensical. If we were to give directions or instructions on how to get somewhere, and we say go 3.2 miles, then go 5.1 miles, then go 1.9 miles, you are so not going to get to the party, because the direction of your distances really is important. If I were to say, come push on this table with 40 pounds of force, well, everybody may not do the same thing. Somebody may have pushed to the right, some person may have pushed to the left. Pushing up is very different than pushing down on that table. So all of these types of forces, direction is very important. And I do like poking fun at Hollywood videos, but I absolutely love this one. There's nothing wrong with it. So let me play this short clip for you.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude.
So we can represent vector quantities with an arrow, and that shape there can indicate both of those ideas, both magnitude and direction. And an arrow can do that nicely. So this would be a vector field map. This would be representing like the velocity of the wind in a variety of locations. So here, these vectors are long, which would represent a large magnitude, and the wind would be blowing fast in that direction. Here, these vectors are short, so the wind would be blowing a lot slower, less magnitude, but right there it's blowing in that direction. And this is a neat vector field map of the wind around a hummingbird as it flaps its wings. And you can see that the wind swirls. The resolution on this is kind of poor, but here are short arrows representing slow velocity, and here there are longer arrows representing a higher velocity. So we'll have some simple questions here. What is similar about these two vectors? And they both have the same direction. What is different? Different magnitudes. And if I were to draw this arrow 7 inches long and this one only 6 inches long, this could represent a velocity of, say, 70 miles per hour, then this one would have represented 60 miles per hour. The magnitude is directly proportional to the length of the arrow. If one of those vectors represented 100 miles per hour and I drew one half as long, it would only represent 50 miles per hour. All right, so we really can take the velocity of one object and add it to the velocity of another object. So here's a plane flying in a very strong wind. And maybe the wind is blowing at maybe 40, 50 miles per hour straight behind him. That would be called a headwind. And you took the velocity of the wind, added to the velocity of the airplane, and then added together to give us pretty much zero velocity. If a person is walking on a train going 4 miles per hour and the train is stopped, then you take the velocity of the train and add the velocity of you get 4 miles per hour. But if you are walking on the train at 4 miles per hour, the train's going 3 miles per hour, your combined velocity would be 7 miles per hour to the right. Person's going to be going 4 miles per hour. The train is going to be going to the left at 6 miles per hour. So 4 plus 6 is really 2 miles per hour to the left. All right, now those seem like easy enough problems, and certainly they are. But what we want to do is develop a technique that will allow us to add velocities in any direction. So here's the technique. If I had a vector here represented by this arrow of 4 meters per second, so if this is 4 inches, that might be 3 inches, but 4 to the right and 3 to the right made 7 to the right, clearly. But here's the technique. The technique is called the head-to-tail method. So if we had a vector here, we would call this end of the vector the head of the vector. This would be the tail of the vector. If we add head to tail, it means we take the head of one vector, bump it right up to the tail of the other vector, and then the resultant is going to go from the tail of the first one to the head of the second one. So 4 plus 3 really is 7. Okay, and we're developing a technique. So that's obvious, but it's going to get more challenging, I promise. So if we had 4 to the right and add it to 6 to the left, we get a resultant of 2 to the left. But again, let's look at the head to tail method. We take the head of one vector, put it to the tail of the other vector, and the resultant is going to go from the tail to the head. Now just be careful, this is called the head to tail method. Here we put head against the tail. But when we draw the resultant, we end up being tail to tail and head to head. The resultant went from the tail to the head. It went from the beginning to the end. Now if I take 60 miles per hour and I add to it 80 miles per hour, you might guess that that is equal to 140 miles per hour. And you would be true, that would be true if you are assuming that those two velocities are added in the same direction. But couldn't we add them in the opposite direction? Like a plane flying this way at 80 miles per hour and a wind blowing that way at 60 miles per hour. Okay, so 60 plus 80 in that sense would be 20 miles per hour. Taking the velocity of the plane, add it to the velocity of the wind. But couldn't we add in any direction? Does the wind have to be just a tailwind coming from behind or a headwind coming from the front? Couldn't it be a side wind? Or a wind at any angle? So in my example here, I am thinking of 60 plus 80 is equal to 100. And we'll have to think, what angle did we add those two things to get them to equal 100? They weren't the same direction, it would have been 140. They weren't the opposite direction, they would have been 20. So somewhere between exactly the same or exactly opposite was the angle we added that. We'll do it with this example here. 4 in that direction plus 3 in that direction results in 5 in that direction. Now my previous examples I was doing this with velocity, But remember that force is also a vector quantity. So 4 pounds that way plus 3 pounds that way results in 5 pounds that way. And you might be thinking, what? Well, go back to that technique that seemed pretty simple, but now we're just applying it to a little more complex situation. You take the head of one vector, put it to the tail of the other vector, so you added them head to tail. The resultant is going to go from the tail to the head. Okay, so we get the vector in that direction. Now, how did we find out the magnitude of it? Well, if these were at right angles, then we could have used Pythagorean's theorem. A squared plus b squared square rooted would have given us c here, 5 pounds. Now, what does that mean? Does that really have any physical reality? If I had 4 pounds there and 3 pounds there, that's the same as 5 pounds there? Well, think of like a hockey puck on a lake, and 2 different people hit that hockey puck at the same time. One person hit it with 4 pounds of force that way. Another person hit it with 3 pounds of force that way. That would be identical. It would be equal to as if one person had hit that hockey puck with 5 pounds of force in that direction. So 4 plus 3 equals 5, surprisingly enough. 4 plus 3 equals 7 when you add them in the same direction, but 4 plus 3 added at right angles to each other equal 5 pounds. Okay? There's another method that we could use, and it's called the Parallelogram Method. It's essentially the same thing, but instead of putting one vector, the head of one to the tail of the other, you put them tail to tail. Now, if you're going to draw a parallelogram, opposite sides of that quadrilateral are going to be parallel, and they're also going to be congruent. So if I knew what one side was and the other side, I could use those 2 sides to draw in the rest of the parallelogram. This side would be equal to that side, this side would be equal and parallel to each other. So when we draw them tail to tail, the resultant is going to end up being the diagonal of that parallelogram. It's just a matter of which one you have preference over. Head to tail or tail to tail, also known as the parallelogram method. And if we had just moved that one over here, yeah, you see we would have gotten the same thing. We can do this with more than one. Come on, it'd be fun. If we have 6 pounds in that direction and 4 pounds in that direction and 7 pounds in that direction, clearly that is equal to 5 pounds in that direction. Maybe it's not so clear. Maybe we better use the head to tail method to show that. So we could take the head of one vector, put it to the tail of the other vector, and then now we're just going to take the head of this vector, put it to the tail of the other vector, and we would draw the resultant that goes from the tail of the first one to the head of the last one. All right, now how did I come up with these numbers? Well, for now, the only technique you might know would be just using a ruler, because the length of this represents the magnitude. We would have to have very carefully drawn this on a suitable scale. Maybe draw this 6 centimeters long in exactly that direction, draw this 4 centimeters long in exactly that, 7 there, and then if we had measured with a ruler, we would have found that would have been 5 centimeters long, which would have been proportional or representative of 5 pounds. So, and then you can add in any order as well. You know, normally 6 plus 4 plus 7 would give us the same thing as 6 plus 7 plus 4 if we just did it with scalar quantities. But it does work with vector quantities as well. Instead of taking the yellow and putting it to the blue, let me take the yellow and add it to the green, then add it to the blue. And still, the resultant goes from the tail to the head. You can put them overlapping each other and see that it really was the same thing. So vectors can be added in any order as well. And it does have physical meaning. If 3 people were to hit that hockey puck at the same time, one person hit with 6 pounds that way, 7 pounds that way, 4 pounds that way, it's the same thing. It would behave identically as if one person hit with 5 pounds in that direction. 2 plus 2. That seems like an easy problem. And before today, you would have said 2 plus 2 is equal to 4. I'm saying that 2 plus 2 is equal to 2. And in my mind, that is true. And indeed, it is true. My question, though, is at what angles would we have to add 2 and 2 to get 2? Well, if I had 2 miles per hour that way and add it to 2 miles per hour that way, now you may have been tempted to say they were at right angles to each other, but it wouldn't quite be right. It's going to equal this, and here's why. Head to tail. Take the head of one, put it to the tail of the other. The resultant is going to go from the tail of one to the head of the other, and because the resultant of all those is an equilateral triangle, it must have been an equiangular triangle. Each of these angles must have been 60 degrees. So 2 plus 2 really is 2, as long as we add 2 and 2 at 60 degrees to each other. All right, can you really take velocities and add them like that? Well, what if we had an airplane flying through calm air like this? And that would represent the airplane's velocity. But now, so that plane was flying north, but now there's a wind blowing to the east. And that wind may have been a little less than half the velocity of the airplane. Well, as that airplane points due north and tries to fly due north, it would be drifting to the east due to the velocity of the wind. And we would like to be able to find out, well, how fast is it actually going? If the wind were blowing further or faster, then the plane would be really, really drifting to the right. But if I knew this velocity and I knew that velocity, if it is at right angles, then we thank our good friend Pythagoras, and we can add those two with Pythagorean's theorem. This velocity squared plus that velocity squared would equal that velocity squared. Here's a plane coming in for a landing, and think about what it would be like to be a passenger on the left-hand side of that airplane, looking out the window down the length of the runway. Yikes! Straightens out at the last moment and lands, but that was a big crosswind landing. The plane was flying this direction at some pretty good velocity, and you're that passenger here looking down the runway. Okay, so this would represent the velocity of the airplane. What was the velocity of the wind? Well, I think it must have been something like that. Because if you take the velocity of the airplane and add to it the velocity of the wind, you want a resultant velocity down the length of the runway. And I think that pilot did an excellent job. All right, now we're going to do the exact opposite. And we have to introduce a new term here. So what do you call the parts of a computer? If you're going to build your own computer and you're going to build and buy the individual parts, you call those parts the components. So what we've been doing is we've been taking two vectors, combining them to make one vector. So the two vectors combined to make the one vector. Vector resolution. We're going to resolve that vector into its components. It's going to be just the opposite. We're going to take one vector and we're going to break it up into two parts. We're going to find its components. So if this was wind blowing north and east, or you could say to the right and up, to describe that direction, well, part of its velocity was to the right, and part of its velocity was up. So here's what we do. To draw that vector, to draw the components, you start at the tail and draw one perfectly horizontal, stopping when you get perfectly vertically in line with the head of the original vector. And then the vertical component is going to just go straight up from there. Well, just like we did here, the green one plus the blue one results in that vector. So if we were to break that vector up into its components, this vector really is the same as this one and that one combined. So if we had a vector here, you say, hey, that's a little bit to the right and a lot up. This one here would be, oh, kind of maybe to the right and down. This one would be to the left and up. And this one would be to the left and down. You could have drawn the up first and then the left, and it would work as well. So if I had this vector here and it's pretty horizontal, most of its component is to the right or horizontal. Very little of it is in the up direction. But as this angle gets bigger and bigger and bigger, we get more component up and less component horizontal. And just as we change, those two vectors always add together to give us our resultant. So a plane is flying like this, and it would be flying north and west. There is a component north, there is a component west. If the wind is blowing to the right with the same velocity as this component, the plane would be able to fly straight north like this. Okay. What did the little shrub say when it grew up? Where'd that question come from? Well, there the shrub grew up and it says geometry. 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 All right, that was just a little thing to introduce, not so much geometry, but maybe more trigonometry, special right triangles. So if I had a 45, 45, 90, and this side was 1 meter long and that side was 1 meter long, hopefully through your experience with algebra, probably algebra 1, you can get into and find that this is the square root of 2. And Pythagorean's theorem would tell you that that's true. If we had a much bigger one and this was 3 and this is 3, this side would be the shortest side times the square root of 2. In general, whatever this side is, this side would be the same, and this would be that times the square root of 2. I'm getting into this now because I'm going to show you some typical problems that you might typically see. 30, 60, 90, because sometimes we'll take a vector here and we'll add a vector here and it's at a 30-degree angle like that. We can find the hypotenuse using these ideas of special right triangles. If this is the shortest side, that's opposite the smallest angle, the largest side is going to be opposite the largest angle, and the hypotenuse is going to be twice that. Hopefully you remember what this is, maybe a little jog for your memory, but the square root of 3. That squared plus that squared does equal that squared. So if we had one twice as big, here, here, and there, in general, whatever this is, the hypotenuse is twice that, and the medium length side here is going to be the shortest side times the square root of 3. The big point here is that if these angles in this triangle are the same as these angles in this triangle, the ratio, and here this is really important, the ratio of any two sides would be the same. So if this is a 30, 60, 90, this side divided by this side would be the same thing for any triangle that has a 30, 60, 90 degrees angles in there. If this is 30, then opposite over hypotenuse would give us the same result. So this was a 45, 45, 90. This was a 30, 60, 90. This might be a little funny, but these turn out to be the angles for a 3, 4, 5 triangle, or a 6, 8, 10, or a 4, 16, 20 triangle. But any triangle with that angle there is going to have the same ratio of sides. And that brings us to SOHCAHTOA. Hopefully you've seen that in algebra somewhere. If not, I'm sure there's a video you can find on that somewhere. Sine stands for opposite over hypotenuse. Cosine stands for adjacent over hypotenuse. And tangent is opposite over adjacent. These are ratios that are stored in our calculator. Our calculator knows the ratios of any two sides for any angle right triangle. So if I had a vector here of 250 meters per second and was at a 30-degree angle, we can find components to the right and a component up. And I'd like to be able to go ahead and find out what those components are. Sine and cosine are going to do it for us here. We need to use an equation that involves the ratio of sides we're looking for. So the sine of this angle is equal to opposite over hypotenuse. The sine of 39 is opposite over hypotenuse. I'm trying to get y by itself. I'm trying to solve for that. So I'm going to multiply both sides by 250. And it looks like I can find out what y is by just taking the 250 meters per second and multiplying by the sine of 39 degrees. If this is in degrees, we have to make sure our calculator knows that that 39 was degrees, not another unit like radians. So we have to make sure we're in degree mode. If we did that right, we should get this answer here. To find out what x is, we have the cosine of this angle is adjacent over hypotenuse, and same thing happens here. Cosine is adjacent over hypotenuse. We're going to solve for x, multiplying both sides by 250, plug that into our calculator, and we get this. But what that means is if we shoot something at 250 meters per second, horizontally it would be traveling 194 meters per second. Vertically, it'd be traveling 157 meters per second. That situation is very, very, very common. So common that if you apply SOHCAHTOA, you do this step, but the very next step would just be coming straight to here. And we're going to do this again, and I'm not going to labor the point much right now, but this is the step I'd like you to just be able to go straight to, skipping this step and going straight to that step. If I knew the sides and I wanted to find the angle, okay, the cosine of this angle is adjacent over hypotenuse. We're trying to get the angle by itself. We got to get it out of the cosine, so we have to do the inverse. We don't divide both sides by cosine, we find the inverse. So it'd be shift cosine of that ratio, and that's our answer. If I wanted to find out this angle, I could use the cosine of this adjacent with that hypotenuse, and that's the answer we would get there. Let's do this problem, and this then will be finished here. But if this plane was trying to fly north and the wind was blowing to the east, it would miss its destination if its destination was straight north. So let's say that this plane is capable of flying 200 miles per hour, and the pilot wishes to fly due north. But there's an easterly wind blowing at 80 miles per hour. What angle should the pilot adjust his or her course? So we know we need to angle to the west here a little bit and fly in that direction at 200 miles per hour. We're trying to find out what angle that is, so that when we take the velocity of the airplane, add it to the velocity of the wind, it results in a velocity going due north. Well, we want to find out what that angle is. We know the opposite side. We know the hypotenuse of SOHCAHTOA. Looks like sine is going to be our right ratio to use. So the sine of that unknown is opposite over hypotenuse. When I use the inverse sine, and that 80 divided by 200 is that decimal, we get this angle here. So now, that's how we have to go to the west of north by that degree. But how long is it going to take to get to that destination if the destination is 450 miles away? Well, the thing is, we're not flying at 200 miles per hour. That's how fast we're going through the air, but that's not our resultant velocity. We have to use Pythagorean's theorem to find out this side of the triangle. So we use Pythagorean's theorem, 200 squared minus 80 squared, square rooted, is that velocity there. That's how fast we're flying due north. That's the velocity. This is the distance. And we can find the time by taking distance divided by velocity. 2.45 hours is how long it's going to take. That's an introduction to vectors and a little bit of review on trigonometry.